Sometimes you may have seen transmission line of length lambda by 4 connected in between the antenna and the feed positions. These are usually used for the impedance matching. This is known as quarter wave transformer. So in this video, let's see what is the importance of quarter wave transformer and what are the things to be taken care while designing a quarter wave transformer for the antenna feeding. Let's see. In our previous video, we have seen that if the load impedance is not matched to the source impedance, that is Z0 is not matched to ZL, some part of the wave will be reflected back. And to avoid that, we should have some impedance matching network so that the total impedance of the entire system consisting of the impedance matching network and the load impedance will be equal to the source impedance, and it can avoid the reflections and maximum power transfer can happen. So the quarter wave transformer is one of such matching network. The main characteristics of quarter wave transformer is from the name itself it shows that the length should be lambda by 4 quarter wave. That is, the length should be lambda by 4 in this case. And it is a transmission line of the length lambda by 4 connected between the load and the source. Another important characteristics of this quarter wave transformer is Z1, that is the impedance of this transmission line. It is very essential to understand this impedance because this plays an important role in impedance matching. So let's see how we can calculate the impedance of this quarter wave transformer or what it should be to provide the impedance matching. So let's see that. So if we consider this case, that is the load impedance and the quarter wave transformer, the input impedance of this total system, that is this entire system consisting of the load impedance and the quarter wave transformer, can be given by Zin of L equal to Z1. Z1 is the characteristic impedance of quarter wave transformer into ZL, which is the load impedance, plus JZ1 tan beta L divided by Z1 plus JZL tan beta L, where L is the length of the transmission line. So in this case, the length is given by lambda by 4. L is equal to lambda by 4. And beta is given by the expression 2 pi by lambda. So this is the expression for calculating the total input impedance of this system. So as we know that L is lambda by 4 and beta equal to 2 pi by lambda, by substituting that, we can see that this expression will become like this, because beta is equal to 2 pi by lambda and L equal to lambda by 4, and this will result in cancelling these things, and the expression will be reduced like Zn of lambda by 4 equal to Z1 into ZL plus JZ1 tan pi by 2 divided by Z1 plus JZL of tan pi by 2. If we consider the tan distribution, we can see that with respect, so this is a plot showing the tan D with respect to D value, that is here beta L and tan beta L plot. Here you can see that when beta L is pi by 2, you can see that tan of pi by 2 is extending towards infinity. So the total expression will be reduced. That means that this tan pi by 2 value is extending to infinity. So that will result in this value will be higher values. So that will result in this expression. So if we simplify that, we can see that Zn of lambda by 4 become equal to Z1 into JZ1 by JZL, which will equal to Z1 square by ZL. So this is the expression for the total input impedance of the quarter wave transformer. So this is our expression Zn of lambda by 4 equal to Z1 square by ZL. And We know that if this system is matched to the source impedance, that is, if Zin is matched to source impedance, there won't be any reflection. That is based on this expression, because the total reflection can be given by, for this system, the total reflection can be given by uh, reflection equal to Zin minus Z0 by Zin plus Z0. If this Zin equal to Z0, then the reflection is equal to 0. So this is the condition for the impedance matching. So this is actually the condition. That means that Zin, that is the total impedance of this system, should be equal to Z0. So when you substitute Z0 here in Zin, we can see that Z0 equal to Z1 square by ZL. So from this expression, we can calculate the impedance of the quarter wave transformer. That can be given by the expression Z1 equal to square root of Z0 into ZL. That means that if a quarter wave transformer to be work as a impedance matching network, it should have an impedance of geometric mean of the load impedance and the source impedance. That is, geometric mean of load impedance is ZL and the source impedance is Z0. If that happens, this quarter wave transformer can provide the impedance matching, and it will not cause any reflection, and it will be like uh, supporting the maximum power transfer. So simply we can say that quarter wave transformer is a transmission line having length of lambda by 4 and the characteristic impedance Z1 equal to the geometric mean of the load impedance and the source impedance. So if these two conditions, that is the length and the impedance conditions matters for a transmission line, it can act as a impedance network in between the load and the source. So let's see what are the main characteristics of quarter wave transformer. It has some limitations because we know that the length of the transmission line is given by lambda by 4, as it is depending upon the wavelength. It can only be used for a single frequency, right? Because we can design this transmission line only for a single frequency. That is, it can only be used for narrow band usage. Also, it can only be used if this load impedance is purely real, or if it has only like real part of impedance, that is like resistive part only, we can use the quarter wave transformer. So these are the two main characteristics of quarter wave transformer. So in our upcoming videos, let's see how we can use the quarter wave transformer for this impedance matching of the patch network, and how we can identify the impedance Z1 using the Smith chart. I hope you get some idea about quarter wave transformer. Thank you.